And artificial intelligence is never really taught. No one sits it down and explains grammar or physics or how to write a poem. Instead, it is shown an almost unimaginable amount of text and forced, over and over, billions of times, to play one stupidly simple game. Guess the next word. Every time it guesses wrong, an automatic process reaches inside it and nudges billions of tiny numerical dials, just slightly, so that next time it will be a little less wrong. That is the whole secret. There is no understanding being poured in, no rules being written down. There is only relentless, mechanical error correction at a scale no human could survive. And the strangest part, the part that should give us pause, is that it works so well the people who build these systems often cannot tell you exactly what the machine has learned, or how. So let us open it up. How does an AI actually learn? Start with what is actually inside. A modern AI is a neural network. Layers of simple math joined by numbers called weights, often hundreds of billions of them. Think of each weight as a tiny dial. At the very beginning, before training, every dial is set at random, and the network is useless. Ask it anything and it produces gibberish. Learning for this machine means one precise thing: finding the right setting for all those dials. To do that, you need a way to measure how wrong it is, and that is the loss function, a single number that is high when the output is bad and low when it is good. The entire goal of training is to make that one number as small as possible. Everything the AI ever learns is the side effect of relentlessly driving its own error score down toward zero. How does it tune billions of dials in the right direction? With two ideas that are the real engine of the AI age. The first is backpropagation. After the network makes a guess and we measure the error, backpropagation works backward through every layer and calculates, for each individual dial, which way and how hard to turn it to reduce that error, using nothing more exotic than the chain rule from calculus. The second is gradient descent. Picture the error as a vast landscape of hills and valleys, with the network standing somewhere on a slope. Gradient descent simply takes a small step downhill toward lower error, then measures again, then steps again. Do this billions of times, across billions of examples, and the network slowly walks itself down into a valley where its guesses are, astonishingly, usually right. No one tells it the answers. It feels its way downhill, one tiny correction at a time. For a large language model, the chatbot kind, this happens in stages, and the first and biggest is pretraining. The model is fed a huge slice of human writing, books, articles, code, much of the public internet, trillions of words, and set loose on that one game. Predict the next word. Show it the cat sat on the, let it guess, reveal that the answer was mat, measure the error, adjust the dials. Repeat for months across thousands of specialized chips. Nobody labels this data by hand. The text is its own answer key, which is why it can scale so enormously. And here is the quietly profound part. In the mere act of getting good at predicting the next word, the model is forced to absorb grammar, facts, reasoning patterns, the rhythms of argument, even a rough model of the world, because all of those things help it guess better. Understanding, of a kind, falls out as a byproduct of compression. But a raw pre-trained model is just a brilliant autocomplete. It will happily continue your sentence rather than answer your question. So 2 more stages, shape it into an assistant. First, supervised fine-tuning. It is shown many high-quality examples of questions paired with good answers, teaching it the format of being helpful. Then the famous one, reinforcement learning from human feedback, or RLHF. Here, people are shown several of the AI's answers and asked to rank them best to worst. Those rankings train a second AI, a reward model, to predict what humans prefer, and the main model is then tuned to chase that reward. This is where the polite, helpful, agreeable personality comes from. But notice the catch hiding inside it. The model is being optimized to produce answers people rate highly, which is not the same as answers that are true. Teach a system to be convincing, and you should not be surprised when it sometimes learns to bluff with total confidence. Why has all of this exploded so suddenly? The uncomfortable answer is mostly scale. In 2020, researchers at OpenAI led by Jard Kaplan found something they called scaling laws. Make the model bigger, feed it more data, give it more computing power, and its error drops in a smooth, predictable curve. There was no clever new theory of thought, just a recipe that kept working as you poured more in. In 2022, a DeepMind team refined it with a model named Chinchilla, showing that many giant models were actually starved for data, and that the compute is best spent on roughly 20 words of training for every parameter. And as models grew, researchers reported emergent abilities, skills like arithmetic or translation that a smaller model simply cannot do and a larger one suddenly can, appearing as if a switch had flipped, though there is genuine debate about whether that is a true leap or partly an artifact of how we measure success. Either way, the headline is humbling. A great deal of modern intelligence came not from understanding the mind, but from making the machine bigger. It is worth feeling how lopsided that is against us. A human child learns what a cat is from a handful of examples. A large model may need to see the word, and the patterns around it, countless times, consuming more text than a person could read in 100,000 lifetimes, and burning through specialized hardware and electricity worth tens or hundreds of millions of dollars in a single training run. It is a brute force kind of learning, wildly less efficient than a brain, that wins by sheer volume and speed. The machine is not better than the child at learning. It is simply able to fail far more times, far faster. And that leads to the most unsettling fact in the field. We can describe exactly how an AI learns, the dials, the loss, the long walk downhill, but once it is finished, we largely cannot read what it learned. Those hundreds of billions of trained weights are not organized into neat rules a person can inspect. They are a dense, tangled web of numbers that somehow encodes everything the model knows. Researchers genuinely argue over whether a model is reasoning or just memorizing, and the honest answer is that it does both, sometimes reproducing training text word for word, sometimes solving problems it has plainly never seen. An entire young science, called interpretability, exists just to reverse engineer these systems after the fact and figure out what concepts are hiding in the weights. We did not write these minds. We grew them, through a process we understand, into something we are still struggling to read. So how does AI actually learn? Not by being taught, but by failing at superhuman speed, billions of times, guided by nothing but the drive to make one error number smaller. It plays an endless game of guess the next word against the whole of human writing, nudging its dials a fraction with every miss, until patterns we would call knowledge precipitate out of the arithmetic. It is closer to evolution than to education, closer to growing a thing than building it. And that is exactly why these systems are so powerful and so hard to fully trust. We design the way they learn, but not the things they learned, and we are only beginning to look inside and ask what exactly is in there.